Okay, so now we move on to chapter 3 of the textbook. Color. So we're on chapter 3. That is about Rademacher complexity. And growth function. And VC dimension. Okay. Color this. So that's the topic that we're gonna study here. So what's the motivation of studying all these things? Okay. We look at whenever we study a new machine learning algorithm, we will try to analyze its behavior. But just like what you saw before, ideally, if PEC learning framework applies, that's great. But it's just like we discussed in the last lecture or last 2 lectures, the typical scenario, the problem is not PEC learnable. One of the reasons is we cannot really find a hypothesis that has as little error as possible. That kind of things may never happen. There is a lower bound of the error that we can achieve. So in most of the typical scenario, instead of showing some problem is PEC learnable and try to come up with a learning algorithm, instead we design a learning algorithm which we believe reasonably good, and we analyze the learning algorithm. Analysis. Learning algorithm via generalization bound. So what does this mean? This means that we will try to prove some facts about the algorithm or some fact about the problem. And then the kind of things that we're going to prove is of the form. We have probability of risk or the real error that we care about. So this is a generalization error. Something risk we care about. For some hypothesis H, we're going to prove that is with high probability that is going to be bounded by some sample estimates of this error, which is an empirical error of H, together with some extra term. That extra term typically have a 2 component that may be tied together by square root, but typically have a 2 components. One component is going to be about, so we have 2 components, one and the other. And then that's a high with a high probability. Now, the bound that we're gonna use in the analysis of the learning algorithm will be typical uniform bounds, which means that we have universal quantification for all hypotheses in our hypothesis class. So what does this mean? This means that once we prove this uniform generalization bound, we can actually, and then say something about our learning algorithm. When we run a learning algorithm, the learning algorithm will do something with the sample. So it will produce some results. We can, by executing the learning algorithm, we can measure this quantity that I just highlighted. And now from this the highlighted part, and this learning guarantee. But I mean, this upper bound tells us we can actually deduce some fact about our ultimate goal, which is this quantity. Okay. Because I mean, that's a probabilistic bound, so it may fail sometimes, but with high probability, we can say the real error that we can, I mean, that this specific hypothesis, our algorithm came up with, is going to be bounded by the empirical error that we can measure with some extra term. Okay. So that's the approach that we're gonna take. And this approach will allow us to provide some theoretical guarantee of the outcome of the learning algorithm. Now the question is, what this F and H actually look like? And now let's make this problem a little bit more explicit. So the sample S will be sample from distribution D, which is unknown. So this is an unknown distribution. So this upper bound F, I mean, ideally, it should, by uniform upper bound, we mean that this F and H, F and G do not depend on small h. Okay? So it applies to everything in the hypothesis set, capital H or curly H. So the parameter of F, okay, and then this small f, it usually measures the complexity of our hypothesis class with respect to the problem that we have right now. And then G is more related to the I mean, some error that's coming from estimation, sample-based estimation. And so what we're gonna care more about in this chapter is this F part. And I mean, in the most informative case, F can take parameters like small m and sample S, even distribution D, and capital H. It cannot take a small h because we want a uniform bound, but it can take all these parameters. I mean, if D accounts for, it's a distribution for input and output, having D is enough. If D is only distribution for the input, maybe there's just some extra parameter coming from C. And in fact, in the last, one of the big results that we proved in the last chapter was have this form, which was the generalization bound for, finite, inconsistent or potentially inconsistent hypothesis set. And in that case, we have this term. That term looks a bit like, I think, square root of 2m and either log of the size of h. So I may be wrong, but it has of this one, square root of log of the size of h. But now, what we're gonna do is we will actually try to do something more general, something more, something is more powerful than the one that we discussed, we deal with before. So what's the problem of this results that the problem is that if the hypothesis set h is infinite, then log of h, size of h, is going to be infinite. So this bound doesn't say anything. The infinity upper bound is useless. So what we're gonna develop in this chapter is something that can also work for the infinite set. That infinite set can be uncountably infinite, doesn't really matter, but we will have some quantity. Essentially, we will learn some function f together with the corresponding generalization bound, and then that function f intuitively measure the complexity of our hypothesis class, and then with that function we will prove that there's some form of generalization bound. And then the three things that appeared in the title of this chapter, which is Rademacher complexity, and also growth function, and VC dimension. They are all about complexity of H. It's some mathematical concept that measure the complexity or expressiveness of H. But they are, they use a different, what I call levels of abstraction. For the Rademacher complexity, I said this function f. So essentially, all of them are about this function f. Now, for function f, we can design a function f such a way that it depends on m, s, d, and h, all of them. Okay, that's one possibility. And then if f depends on all of those parameters, it's maybe very hard to compute because, if function f only depending on, say, the first parameter m, maybe it's a lot easier. It should be a simpler function than the function f that uses all of those parameters. And then intuitively, the first, second, and third parameter, they are about the problem. Okay, actually D is about the problem. So this. So the D part is about problem. What? Sorry. Just write the D. So the D part is about the problem. It's what kind of a learning problem we have. So D may be distribution over the input, or maybe D together with, if C is also there, their combination is really specifying this is a specific learning problem we want to solve. And then the other component, which is M and S, they are about the inputs to the problem. Okay. And then finally, we have H. Okay. So some of the concepts, we will learn two versions of Rademacher complexity. The one is called empirical Rademacher complexity. The other one is called just Rademacher complexity. Some of the concepts like Rademacher complexity is very precise. It can, depending on the problems, like it can depend on distribution D and C and MNS. So it gives a much more informative measure about our hypothesis class. So it's saying a bit like our hypothesis is very complex with respect to this specific learning problem that we are given. On the other hand, growth function and VC dimensions are much more abstract. So the Rademacher complexity uses all the quantities. It uses nearly all info. But for VC dimension, it's only going to use the parameter H. So VC dimension doesn't really know what kind of problem we are talking about. It only measures the complexity of our hypothesis class. So you can get a feeling that, VC dimension is much easier quantity to deal with, but the generalization bound we're going to get in the VC dimension is more approximate. Growth function is somewhere in the middle. It only depends on M and H. Okay. So this Rademacher complexity, it depends on all of M, S, and D, and H. So we're gonna learn these concepts, and then they are all different ways of defining this function F, but they have a different levels of abstraction or different levels of informativeness. If it's much more informative, that gives a tighter bound. On the other hand, it's more difficult to deal with. And if it gives less information, the bound will be loose. On the other hand, it's much easier to deal with. Okay. So what we will perhaps look at today is Rademacher. We'll focus more. We only look at Rademacher complexity today. Okay. So next part. So let's go directly to the definition of Rademacher complexity. So look at Rademacher complexity. Rademacher complexity is a very general concept. It can be applied to any other setting. So we will. So it's a measure about how complex a function is with respect to some distribution. So here's a setup. So the setup where we talk about, so it intuitively measures the complexity of a set of functions. Well, you can say it's the expressiveness of set of functions. So because it's going to be applied to not just our hypothesis set, but also some other set of functions that's induced by the set of applied from the hypothesis set, I'm going to use a different notation. That notation is going to be written as f, which is a set of function that goes from input. Input doesn't have to be same as this inputs from the learning problem. So depending on this set of function, it will vary. So we will use u just to avoid the confusion. And then output, we will just write at v. Okay. And then v is typically a subset of the set of real numbers. And so one example is u can be input space, and then v output can be output space, which may be equal to 0, 1, or -1 and +1, and so on. Then f may be whole hypothesis set. So that's one possibility, but there's a different possibility. So u may be x times y. So this set of function f can be anything. So this can be anything. So u can be x plus y, and then v can be just values between interval 0 and 1. And then f is induced from L by the following function. You take x and y. It's a function that take x and y and then return the indicator where h of x is not equal to y. It will return 1, otherwise return 0. And this function is determined by h, and h is coming from h. So the f that I just the second example is not exactly we are talking about hypothesis set, but it's something related. Okay, but then this Rademacher complexity applies to any set of functions. And there are two concepts of Rademacher complexity. One is called empirical Rademacher complexity. The other one is called just Rademacher complexity. Empirical Rademacher complexity is defined like this. Definition 3.1. So let S be a sequence of elements in the input U, so that the first example, that's just a sequence of inputs. Second example, that's a sequence of input-output pairs. Okay. So in that case, so S is written as U1, U2, and UN. And then the empirical Rademacher complexity of F is of F with respect to this is defined like this. is written in this form, and F is defined as an expectation over. So this is a m-dimensional vector sampled from uniform distributions on -1 and +1. And then we are computing Sprint of F such that so 1 over m summation I is equal to 1 to m and F of ui. So, I mean, one assumption is that I will always assume that this function set is always non-empty. So this Rademacher complexity, I mean, just the definition, it can be infinite. So that's also okay. But typical scenario, the set of f functions f is bounded, its output is within some range. So the expectation is well defined. Okay, so what does this mean? So that's the formal definition of Rademacher complexity. Yes. So let's talk about empirical Rademacher complexity. And then what does this mean? I mean, intuitively, what that means is that, I mean, this sigma arrow is called Rademacher variable. And then what they say is that, like, whether what it measures is whether the set of function f with respect to this specific inputs s, whether our set of function f can point to any directions. If it's very rich and very expressive, we can point to any direction. So let's think about some simple case where s is just a two real number. No, two elements, u1 and u2. Each of this ui. Okay, it's just two elements, u1 and u2. So in this case, Rademacher complexity uses a Rademacher variable, which is of dimension 2. So sigma arrow, sigma 1, and sigma 2. And then it's a uniform distribution between with in the set -1 plus 1. So there are four possibilities, like -1, -1, +1, +1, -1, +1, +1, -1. Right. So, and then what it computes, the quantity it computes. So let's, okay, the quantity we compute is 1 over 2. And summation of I is equal to 1 to 2. F of, sorry, there was a mistake. Sigma I has to be here. So, yeah, you're right. Somewhere you're right. Sigma I have to be there. Thank you. So it's a sigma I and F of xi. Because that means 1 over 2, sigma 1, F x1 plus sigma 2, F x2. U1 and U2. And then you can view this as an inner product. So it's a vector sigma 1, sigma 2, and then another vector f of u1 and f of u2. Then one thing that you learn in the linear algebra is that if the norm, or in T3, the size of this vector is fixed. And then the one which maximizes this inner product is the one that have the same direction as this vector sigma 1 and sigma 2. So intuitively, what really happens is that for sigma 1 and sigma 2 points to 4 directions. The one is +1 and -1. So this is one direction. Another is the sigma 1 is +1, sigma 2 is -1. So this is another direction. Third and fourth. So there are 4 directions. And then you assign a quarter probability for all these 4 directions and see that whether f applied to specific input u1 and u2, and we can vary this function f. By varying this function f in our set of function, this curly f, whether we can align the resulting vector like this one to all these 4 directions exactly. So if we have the set of function, the curly f is very rich, so it contains lots of functions, then aligning will be no problem. We can just pick some functions that in this direction. Maybe for this, the different sigma, we can find the function of this direction and so on. So then that will lead to the very large value of this empirical Rademacher complexity. So Rademacher complexity, so note that there's a supremum in the definition of Rademacher complexity. So Rademacher complexity intuition is like this. We randomly choose the direction and see that whether our function class of the set of functions allows us to produce vector of that direction. If our function class is very rich, we will exactly align or very close to exactly align the resulting vector, like this one that you see on the slide. And if our set of function is very poor, so in terms of expressiveness, then this alignment will not be possible. So then that will give a very low value of Rademacher complexity. So just to say it again, it's Rademacher complexity defined mathematically, but as you see in the screen, but intuition is we randomly choose a direction and see that whether functions together with the given inputs leads to a vector of that direction. If that's the case, it's a high value. If that's not the case, it has a low value. So, and then the actual Rademacher complexity is defined based on this empirical Rademacher complexity. This. So, definition. The Rademacher complexity. So to talk about Rademacher complexity, we have to assume some distribution. So that D is the probability distribution on input U. So then and some M is natural number of samples. Then the Rademacher complexity of F with respect to Dn. M is just the expectation of empirical Rademacher complexity. So we sample a sequence of inputs independently. Instead of, I think the Bonu asked me why it's not standard vectors. I don't really know. Maybe the results may be similar, but the good thing, so I guess you meant like a 0, 1 instead of -1 and +1. So one good thing about this -1 and +1 is that it has lots of symmetries. So we're gonna use this symmetry. If you see later the derivations of the upper bound, the generalization bound, we'll notice that we are exploiting these symmetries quite a bit. So there's a reason why we are thinking about -1 +1. That's because there are lots of symmetries. So then the actual Rademacher complexity is defined this way. It's an expectation of empirical Rademacher complexity. So it's written as Rm of f. But implicitly, this R depends on M as well as distribution D. Okay, let's color this a little bit. So now I said we will learn the complexity measure for a hypothesis set, a set of functions. Then we learn about two complexity measures here. Okay, the one complexity measure is empirical Rademacher complexity, and the other complexity measure is the Rademacher complexity. Now you can see that both especially the Rademacher complexity definition depends on M as well as distribution D. So it's a very informative concept. It measures the complexity of a function class with respect to a specific distribution. And that we will see that later. We will look at some different definition that will have a different mean. We will not talk, the different definition will not talk about will not depend on the distribution. So let's look at some example. So think about some example. So think about this function f to be some functions that goes from the real number to -1 and +1. And then essentially the functions are defined by a rectangle. So if it's inside the rectangle, we will return 1, otherwise it will return -1. Formally, we can define it like this. F defined to be take an input x and return indicator. Not rectangle, okay, interval. Sorry, it's a much simpler problem. It's interval. So if x is in interval ln r, we return 1. Otherwise, we return -1. So that's written in this way. X is not ln r. It's going to be, because of this minus sign, it's going to be -1. And ln r are just two real numbers. Okay, so that's our class. And here are some exercise together with examples. Then I want you to compute. I will give you maybe 3 minutes, and then I want you to compute empirical Rademacher complexity for the following case. Suppose S1 is equal to, it's a single sequence containing element 3. S2 is equal to 3 and -2. S3 -2, 3 and 5. And S4, 3 and 3. Compute empirical Rademacher complexity. S1 of F, and so on. Okay, I will give you maybe 3 minutes to do this calculation. Okay, so for the first, this 1, 2 case is 1. That is the maximum Rademacher complexity that we can achieve because the value of, the possible value of f, the maximum value is equal to 1. And that because of this is maximum value. And that's possible because for Rademacher variable, for this single input s, the input 3 can be plus and minus, plus 1 or minus 1. And then if it's plus 1 to maximize, we should be able to find an interval that includes the 3. That's possible. You can use the minus 2 and 4 that includes 3. If it's minus 1, we should find some function f that will assign minus 1 to 3. That is also possible if you just pick the interval that doesn't include 3. Okay, so because as far as 3 is concerned, we can find an interval that includes closed interval that includes 3, closed interval that doesn't include 3. Both plus minus case, we can find the exact alignment. So we can find value which have exactly the same sign. So we can achieve the maximum case here. The same thing happens in SEG, this two input case. So if there are 4 possibilities of Rademacher variable plus, minus, and so on. In all those 4 possibilities, we can find an interval that includes inputs labeled with plus, Rademacher variable plus, and then also that the interval doesn't include input that's labeled with minus. Okay, so that's why because of all these cases we can find exact alignments. That's why we can have value 1. In this case, for most of the Rademacher labeling, so Rademacher variable, such as plus, minus, minus, and so on, well, minus, minus, plus, and so on, we can find a function in f that give exact alignment. So for instance, if it's minus 2, 3, and 5, we can use a different color. We can use an interval, some function f that's essentially defined by the interval that includes minus 3 and 0. And then for that, minus 2 will be mapped to plus, 3 and 5 will be mapped to minus. So if you take compute this quantity, that quantity will have a value, this quantity will have a value 3. So if you divide 3 by 3 with this m, then that will have a value 1. Okay, so any in the plus minus minus case, minus minus plus case, there we can achieve the best we can do. However, there are cases where we cannot do this. If it's a plus, and this one is minus, so then we cannot find an interval that include minus 2 and 5 without including 3. The best we can do, best alignment we can produce in this case is include minus 2 and 5. Okay, so we just hit two cases. So in this time, we choose like minus 1 and 6. So there are 2 cases for which we cannot be perfect, and there are 6 cases we can be perfect. So if you do the calculation here, I'm not going to do the exact calculation, but if you do this, consider these 2 cases and compute the quantity that I did in the definition of empirical Rademacher complexity, I think in my calculation it was 11/12. And then the same thing happens in the last case. The input is repeated, but Rademacher variable can be different. So if it's the same, like plus plus or minus minus, we have no problem. We can produce exact alignment, but if it's a plus minus or minus plus, we cannot. So each of them have a probability 1. Each of these Rademacher variable happens probability 1/4. So for 1/4 case, we can achieve exact alignment that will give a value 1. And there are 2 cases. In the other case, each of them have a 1/4 probability. There are 2 cases of this. No, my convention was not. So there are 2 cases of this, and each of these cases what we can achieve is a square 1/2. So if to do the calculation, they will give us, I think, 3/4. And you can kind of feel that, I mean, for this problem and this case, I mean, especially in the S3, our interval is not very expressive to exactly describe some labeling like plus, minus, plus. So that's why we don't have number 1 here. Okay, so that's, I hope, help you to understand Rademacher complexity a little bit. Now let's do the key result. The main result with the Rademacher complexity is the following bound. So theorem 3.3. It's about generalization bound. But here's something quite important. We are thinking about the set of functions. The set of functions goes from input u, but the output is bounded between 0 and 1. So some value between in the interval 0 and 1, including boundaries. And actually, this 0 and 1 doesn't really matter. I will later ask you to generalize this, but it has to be bounded. So there should be with the range has to be bounded. So this means our u and v is equal to 0 and 1. And then that's some big delta, which is about the precision of the statements versus sample size, and also some distribution. Pick a prop over the inputs. So in this setup, so then we have a 2 generalization bounds. The first generalization bound say probability of so for every function in f, the expectation of the function f, where u is a sample from this distribution D, is bounded by our estimates of this expectation, which is expectations u from empirical distribution over S. So S is so M examples from D, drawn from D. So we are thinking about uniform distribution over S. So that's what this empirical distribution is telling us. So this f of u. And the exact formula of this is 1 over m summation I is equal to 1 to m of ui. It's a quantity that we can compute plus 2 times empirical just Rademacher complexity. Of f plus square root of log of 1 over delta over m is going to be greater than equal to 1 minus delta. So 1 minus delta, intuitive way to read it is with high probability for every f, its expectation with respect to D will be bounded by our empirical estimate of that expectation with some quantity involving Rademacher complexity. So that's what the first statement tells us. In the second statement, say something very similar. But instead of using the Rademacher complexity, it uses empirical Rademacher complexity. U bounded by expectation of U. But now we are using empirical Rademacher complexity here. And then now the quantity is changing. So 2 over delta. So here's a way to read. So we will prove this theorem. Right? Hope I have enough time to prove this. We'll prove this theorem. Here's a few things you can read it out. So they just, okay, so this quantity is, maybe some of you might remember, it's a bit similar to the one that you saw before when we used the Hofstad's inequality to derive the generalization bound. Something like this appears. So essentially, we're going to use something like Hofstad's inequality, some generalized version of Hofstad's inequality to prove this theorem. And then you will see number 2. The number 2 is really exploiting the symmetries existing in the definition of Rademacher complexity. We will have some subtraction of 2 quantities, and we will symmetrize it, and so that each of them becomes bounded by Rademacher complexity. So that's why we have a number 2. And one below, things are pretty similar, except that we have a 2 over delta and number 3. This 2 over delta and number 3, they are all coming from approximating or estimate, some coming from the estimation error of this actual Rademacher complexity by empirical Rademacher complexity. Why does the one below important? Sometimes because we don't know the distribution, the Rademacher complexity of the one above cannot be computed. On the other hand, the Rademacher complexity is still useful, the upper bound is still useful, but this quantity is hard to compute. The quantity below, we can actually measure it. Computationally, it may be difficult, but it's something that we can solve in some cases. So the lower bound actually gives us something which we can actually measure. So we run the algorithm, we measure something, the measurement tells us, okay, what we produce by our learning algorithm is this group. Okay. Right. So then how we can prove this theorem? So the proof of this theorem uses so-called Mcdmid inequality. Okay, so let me write this one first. So the Mcdmid inequality is quite similar to Hofstad's inequality. But it's generalized. So in the Hofstad's inequality case, we are thinking about sum of independent random variables. 1 to m. The version I explained to you is normalized, but this normalization doesn't have to appear. Mcdmid case, instead of applying the sum, we are applying some arbitrary, choose a different letter. Let's call it k. So it's not a very symbol with different function k applied to x1 to xn. So k can be sum, but this is like normalized sum. Doesn't really matter, but k can be any functions like this. Okay, and the Mcdmid inequality says xi's are independent. If k has some property, then we can bound. The deviation of this k applied to sample x1 up to xn from its expectation with high probability. Okay. So here's a statement. The statement said we have a x1 up to xm. They are independent random variables. And we have a function k that takes these small values, x1 to xm, and return some real number. But it has some interesting property, which is if we change the value of one coordinate only, then its change is bounded by some quantity c. So I'm going to tell you some simplified version such that if we change one coordinate only, so the one before and after, everything is the same except this xi. And they are going to be bounded by C, okay, some quantity C. So in that case, well, this Mcdmid inequality say, okay, can we say something about the K applied to independent random variable x1 up to xm, and then their expectation? And we said, actually, we can say something. So that K x1 to xm, the probability that this random quantity deviates quite a lot from its expectation by large margin, which is epsilon, is going to be bounded by expectation of -2 epsilon square, and then m times c square. Okay, so that's it means, and then the probability, the same thing, bounded below by -epsilon. That means that our estimate is much larger than the expectation. The one below means our estimate is much smaller than the expectation. They're also bounded by the same probability. So yeah, MC squared. Okay. Right. So that's the Mcdmid inequality, and this is, you can view this as a generalization of Hoeffding's inequality. And in Hoeffding's inequality, we have an independence assumption and a boundedness assumption that appeared. The same thing here going on here. We have an independence assumption as well as we have this boundedness assumption. And they are the reason why we can have inequality like this. Okay. Now let's, the specific form of inequality that we're gonna use is the, okay. So I don't expect you to remember this inequality, but one thing that I want you to remember is that we are applying some function k to a bunch of independent variables, and k is somehow bounded, and they will give us this this bound, and that's what we're gonna use. Okay, now how we use it to prove our theorem, and then the key part of the proof of our theorem is the following quantity. So we look at our theorem, and what we're gonna do is that, so we will, notice. So we will notice that, okay. So really the theorem can be expressed in terms of a supremum. So if you subtract the quantity that I just pointed out by single arrow from the quantity that I pointed out by double arrow, and then take a supremum over with respect to everything in this set capital, the curly F, and the statement of universally quantified statement is exactly the same. The supremum is bounded by the Rademacher complexity and then some extra term. Okay. So what we're gonna do, we will define a function that will directly express the supremum and then do something about this. So here's the supremum that we're gonna define. So we'll define function p of s function p is a mapping that take m inputs and then returns -1 and +1. And it's defined like this. P of s of F, expectation of X U is a sample from D, F of U minus empirical distribution, sample from empirical distribution determined by S of U. So that's the definition, the quantity that we're going to define. So once we define this, then for the first part of our theorem, suffices to show with probability greater than or equal to 1 minus delta, we have B, we can show this bounded by 2 Rademacher complexity of F plus square root of log 1 over delta to M, then we are done. And that's exactly a restatement of the first claim of our theorem. So we replace universal quantification of this set called the F in terms of supremum. And typically for mathematicians, when they talk about the uniform something, what they really mean is just some quantity over the supremum. Now, how we can show this? So our plan is to show the following two. The first, we'll prove that the P of S is bounded by expectation of M. So we are taking expectation of a B plus square root of log of 1 over delta with probability at least 1 over delta. So that is what we're going to show. So then it looks a bit similar to the high probability bound that we have to show, except that instead of having Rademacher complexity, we have an expectation. So next thing we will going to prove is what you expect, which is show that that expectation is actually bounded by Rademacher complexity. And 2 times Rademacher complexity. So that's what we're going to show. So you can see that if you prove both of them, then we are done. Now the question is how we can show the first and the second. The first can be proved by using Mcdmid inequality. So I said Mcdmid inequality applies when we have a function, which in this case corresponds to phi, and we have independent inputs, which will correspond to S. So if you apply the Mcdmid inequality, we will get this bound very easily. And then the second one, how we can show the second, we will use a symmetries. Of Rademacher variables. So that's how we're going to prove this. So let's go and prove both. So for first, here's how we can do this. And so one thing that you can show is the following. So to apply the Mcdmid inequality, the key part, exact numbers, I don't expect you to remember, and maybe it doesn't really matter for you now. Maybe better for you to sit down and do some calculation. But the more important bit is to get the key idea. The key step that's required is to show the boundedness. This S is a sequence of independent random variables, so there's nothing to prove. The only thing to prove is a boundedness. And then the boundedness and also the specific bound actually matters. So the boundedness is the following. So we are thinking about phi applied to inputs. So in my notes, I mixed u and x. So I hope you can understand this. u1 up to ui, um minus phi of u1 to ui prime and un. And then the definition involves Supremum. And then for simple property of the Supremum, this can be bounded by Supremum of, I mean, I'm not showing the details, but this one is easily bounded by this empirical expectation of f of u, because my note is using x, and I keep getting confused. But then the empirical distribution you're using is u1 and ui prime, minus empirical distribution u1 ui un of f of u. Okay. So the key things to notice is that in one you have a ui, the other ui prime, and the other ui, and all the rest are the same. So if you actually compute this empirical distribution, the expectation with respect to empirical distribution, you can actually get the exact quantity. So it's a Supremum f in f over m f of u I prime minus f of ui. And because the value f can, the value of the f is bounded between 0 and 1, the maximum difference between f of ui prime and f of ui can be just 1. Okay? So this is going to be bounded by 1 over m. So now we are ready to apply the Mcdmid inequality. We said changing the only one coordinate in the function phi will induce m-was 1 over m change, and then each inputs will be independent. So if you apply the Mcdmid inequality with this bound, then that will give us exactly the first point that I wrote here. Yeah. Okay. So now for the second part is a bit more interesting. So the second part is just showing this expectation. This is bounded by this Rademacher complexity, and that's more calculation. Here's the calculation. So we're gonna bound this expectation over d over m phi of s. And we unpack the definition of phi of s. It's defined by Supremum of f such that we compute the expectation is from d and compute the empirical estimate. So that's by just unpacking the definition. Now we are making some changes for the first part. So this first part, it actually can be written as like this. Expectation of S prime. So we have an m independent samples, and then we compute u from S prime and f of u. What does that mean? That means, in other words, this quantity, this is exactly the same as this quantity, but we are using different samples as S prime. But what it means is this is the quantity here. On average, it produced the right value. So in other words, it's an unbiased estimate of the quantity that we care about here. So and that's always true. You can easily prove this because S prime is an independent sample. Now, what we do is that we move this expectation. Okay. We move this expectation inside the expectation here. So if we do so, then here's what we get. Yeah, so far I didn't use any symmetries or anything. Instead, set expectation of S prime and expectation of U minus expectation of U. Okay. So now one interesting bit is that if you take expectation from inside the supremum to the outside, the things become larger because the supremum is a complex functions. If you take expectation from inside to the outside, it's larger. Also, you can intuitively understand why that's the case. The maximum of the average surely smaller than or equal to, is going to be bounded above by average of maximums. Every case, if you take a maximum, that will give us something usually larger than the maximum of the average. Okay. So if we take it out, we get larger. So if we do so, we have two samples which consist of m examples. They are independent, S and S prime, S primum of f. Now, if you compute, express this quantity explicitly, it's going to be 1. So what I mean by this quantity, I mean this. So if you express it exactly, that's going to be 1 over m summation of I is equal to 1 to m f of ui minus ui prime. So it's prime here. And then f of ui. So ui primes are from this S prime, so it's a u1 prime to un prime. And both just user ui's are from S and un. Okay. Right. So then here now we are using symmetries. So if you have a SNS prime, okay, this is actually equal to S prime. And we will use a Rademacher variable, which is a sample from uniform between -1 plus 1 of size m. Then that is the same as Riemann of f 1 over n I is equal to 1 to m sigma I ui prime minus f of ui. So what's going on here? So I think the best way to understand is just thinking about concrete examples. So think about example where we sample u1, u2, then we sample u1 prime and u2 prime independently. So they are all independent samples from D. So that's one sample. Another is we do the same thing to u1 prime, u2 prime. But then we sample the +1 and -1 uniformly. So maybe suppose we some point plus 1 here, minus 1 here. So if we get minus 1, we swap these two. Okay? And then the returned thing is u1, u2 prime, and u1 prime, and u2. Okay? So depending on the sign of this Rademacher variable, we don't change anything, but we flipped the values from S and S prime. And if you do so, it doesn't change the distribution. These two guys are defining, so they are two M sequences of input values, and their distribution do not change. They have exactly the same distribution. So doing this trick, so multiplying sigma I here, exactly correspond to flipping. So if you sigma I is equal to 1, nothing happens. Sigma I is equal to minus 1, that means we are really changing ui prime and ui, like this example that I showed you there. And then that will be implemented here by the sigma I having a minus sign. Sorry, maybe I think likely spend 3 to 5 more minutes. I apologize for this. Next time, I'll try to keep my time. Okay. So these two things are equal because of the symmetry and because of this multiplication. So this multiplication really implement this symmetry by saying if sigma I is minus 1, we're going to switch ui and ui prime. Okay. And then now if we have a supremum of two things, then that's bounded by supremum of individual things. So you have an expectation. And then we will separate them out. And here's what we get. Of S prime. F 1 over m sigma n minus f of ui. Here's sigma. Just right. Fix this. Now here we are using symmetry again. So if you take a Rademacher variable, so for this Rademacher variable, if you first sample this Rademacher variable and then just add minus sign, that's not going to change anything. So what that means is we sample Rademacher variable sigma 1, sigma 2, and then flip their sign, minus sigma 1, minus sigma 2. They are different random variable, but they define exactly the same distribution. In other words, they define uniform distribution. So that we can rewrite the second thing as expectation S prime, supremum of f, 1 over m, I is equal to 1 to m, sigma I of ui has to be prime. So I think I messed up. This one is prime. Okay. So this guy is prime. Yes. But now you can see this is exactly Rademacher complexity of f. Also, this is exactly Rademacher complexity of f. That gives us the bound that we are looking at, which is the expectation of B of S bounded above by 2 times Rm of f. So that gives us a proof of the first quantity that we care about. And for the second claim, okay, let me talk about the second claim the next lecture. So I will discuss the second claim and then move on to, so this is very general result that will be applied many times throughout the course, also throughout the textbook. So maybe worth spending a bit more time on it. And then, but we will instantiate this general result to our specific learning problem setting and derive a bit some quantity that's more relevant to us. Okay, sorry for overrunning, the time. And so that's it for today. And thank you very much. I'm gonna be here for about 5 more minutes. So if you have any questions, you can ask me. Okay, so thank you.